So in this class, we will solve another problem on finding the moment of inertia, which is also a model question paper problem. The moment of inertia we have to find out. This comes under module 4 about x-axis. So here he has given a figure like this. It's a composite section. We have to find the moment of inertia of the shaded area. So here you can see the composite section consists of one rectangle portion of dimension 100 mm width by 150 mm depth and a triangle portion of base width 100 mm and height 100 mm, out of which a circular portion is cut. So it's a cutout portion or a whole portion of radius 25. Of course, the circular hole is symmetrically placed in this rectangular portion. Now this becomes the shaded area. That means it consists of three portions. One is this rectangular portion, two is the triangle portion, three is the circular portion. So your area becomes now A1 plus A2 minus A3, like that we have to take. Of course, here we have given the moment of inertia. We have to find out about this x-axis. So always the moment of inertia is calculated with respect to particular axis of reference. So here he has given x-axis. Of course, the dimensions are given in millimeters. Now, for this we have to use a very important rule called the parallax theorem. So solution works like this. So we can directly, without locating the centroid of the shaded area, we can directly write the moment of inertia expression. Only thing is you should be knowing the moment of inertia expression for the individual sections. For example, I will take one by one. So this is B, this is D. For a rectangular section, above its centroidal axis, horizontal axis, suppose this G1, because this is rectangle, I take it as portion 1. So G1 is the centroid of rectangular portion. So if I want to write this G1x, if I want to write this, it will be equal to, otherwise I can write it as Igx1. So like this I will formulate. So Igx1, you know that it is BDQ by 12. So this expression you should be knowing. So moment of inertia expressions for standard sections you should be knowing. Similarly, the moment of inertia of this triangular portion. Suppose triangle is like this. Centroid of the triangle will be here. So this is B. If I take this as B for the triangle and this as H. Now here what I do here is I will take of course if you observe the diagram, this becomes your x-axis with respect to rectangle. Base of the rectangle is x-axis. Similarly, base of the inverted triangle is x-axis. Now I can directly write the expression for this Ixx for this triangle. So I will write it as Ixx2 because 2 is the number I given for triangle. You can directly write. Here I have written for about centroidal axis, but here about the base I can directly write, which is BH cube by 12. So all these formula you should remember. Okay, BH cube by 12 is the moment of inertia of the triangle about its base. Whether it is inverted triangle or straight triangle, the expression is the same. Now the third one is the circular portion. So if you know the diameter of the circular portion, B is the diameter, of R is the radius here. If I take diameter, then expression for the moment of inertia of a circle about its centroidal axis, I will take it as G3. G3, of course your x-axis is somewhere here. So now this expression for Igx3, I will write like this. Igx3 will be pi d power 4 by 64. So these three formulae you should be knowing. So then only you can find out the moment of inertia of this composite section about any required axis, reference axis. So here these three we have derived and you should be knowing this for standard sections. Now let us I will use one important theorem called parallel axis theorem. Parallel axis theorem is used to find the moment of inertia of the composite section about the required axis. Here the axis is x-axis. So please note that here x-axis is at a distance of, in this case, in the case of this triangle, this x-axis here, centroid of the rectangle will be here. So this distance is 75. Okay. But whereas here x-axis coincides with the base of the triangle, so distance is 0. Whereas here x-axis is distance of once again 75 from the center of the circle. So let us write down these values now. Now, according to parallax theorem, it states that you have any figure, then figure like this. This I have explained and proved in one of the earlier videos. You can go through that. So here I have a centroidal axis. Gx is the centroidal axis. It is the centroid of this area. Supposing this area is A, and the distance between this centroidal axis and a parallel centroidal axis, AB is, let us say AB is the parallel centroidal axis, which is parallel to the dx axis. So distance between these two is yc. Then according to parallax theorem, if at all you want to find IAB, moment of inertia of the area about any parallel centroidal axis, it will be equal to IGX, moment of inertia of the area about its centroidal axis, plus area of that portion into yc square, distance square. So this is the parallax theorem. Now using this parallax theorem, we can find out the moment of inertia of this composite section. Now let us write down for individually for the rectangle portion. Now what happens here? If I want Ixx, Ixx is the moment of inertia of the shaded area about x-axis. So this is the unknown now. So this is what we have to find out now. But this consists of three moment of inertia expressions. One for the rectangle. So I will write it as Ixx1. This is for the rectangle. Plus second one for the triangle. Ixx2. This is for the triangle portion. Minus Ixx3. This is minus because circular portion is a cutout portion for the circle. So this is the expression. This is minus because it is a cutout portion. Even in the case of centroid also, that since area is negative, we are going to delta the area. Here, since it's for a cutout portion, moment of inertia is negative. That I have explained earlier. Now, we will find out these three separately, then we will substitute. Now, I call this as 1. One by one we will find out. So first I will find out Ixx1, that is for the rectangle. Now observe here, all of you observe here that, so I am using this parallax theorem now. Now I will compare this diagram now. So here you can see that if you observe these two, x-axis becomes your AB axis and the centroid D becomes D1 here. So therefore what I can write here is Ixx1 will be equal to IGX1. Here it becomes IGX1 plus A1. A1 is the area of this rectangle portion into YC1 square. This is how. So 1 stands for rectangle. Please note that 1 stands for rectangle. Now here, what is the area of this rectangle? So A1 is here 100 by, this is 100 by 150. So B is 100. Of course, D is 150. So this is the area, millimeter square. So now, what is the value of YC1? YC1 is this, 75. There is a distance between the centroidal axis and the x-axis. Please note that x-axis is nothing but AB axis here. It is called as the parallel centroidal axis. Now therefore, what I can write here is IGX1 is nothing but BD cube by 12 here. Please note, BD cube by 12. So B is 100 into D is 150 cube divided by 12. plus A1 is 100 into 150 for the rectangle, 100 into 150 into YC1 is 75. So 75. So this is the expression for Ixx1. Ixx1 is nothing but moment of inertia of the rectangular portion about x-axis. One stands for the rectangle. So the value we are going to get here is 1125. Please take the value 1125 00 000. And you know that the unit for moment of inertia is millimeter over 4. So this is the value of Ixx1. So one value we got here. The second one is for the triangle. For the triangle, I will write that as Ixx2. Ixx2 is the moment of inertia of the triangle about the x-axis only. So here also same formula is valid. Only thing is it is Ig. Okay. Here what I will do here is you need not use parallax theorem here. Yeah, correct. So Ixx2 directly you can write it as bh cube by 2. So about the base itself I know the formula. bh cube by 2 for the triangle is, for the triangle B is 100. This is B. This is H. So 100 into 100 cube, 100 into 100 cube divided by 1. So that's all. So this is about the base itself. So the value for this is I will take it as 8333. 8333. 83 lakhs 33,323 millimeter power 4. So directly you can get. So Ixx1 we got, Ixx2 we got. Next is Ixx3, that is for the circle which is negative. So you should be careful. It is negative. So what I will do here now, I will write the third expression for the circle. So third one is for the circle. For the circular portion, circle, you know that Ixx3 is the moment of inertia of the circular area, circular portion about the x-axis. Once again, we have this parallax theorem here, which is nothing but Igx3 plus A3 into YC3 square. See, please note here, Igx3 is this pi d power 4 by 64. So pi by 64 into diameter, radius is 25 mm, diameter becomes 50. So 50 to the power 4 plus area of this circular portion A3. So A3 is pi d square by 4 or pi r square. You can write pi r square. So pi into 25 square. R is 25. So this is the area. So I can write here as pi into 25 square is the area, A3 is that, into YC3 is this distance, so 75. Distance from the central axis of the circle to the given x-axis, that is your YC3 75. So this is 75 square. So this is the value of Ixx3. If you simplify this, you are going to get 113. Please check the value 45700. For decimal I have omitted. Yeah, 1,13,45,703 millimeter power 4. We will include the values because it is millimeter power 4. Now we got all the three values. Now if you want the expression for the answer for the moment of inertia of the composite section. Composite section moment of inertia is now Ixx is nothing but this one. I have written here. You just substituting the values in 1. So you are going to get the value of Ixx of the moment of inertia of the composite section or the shaded area about the x-axis. It is Ixx1 plus Ixx2 minus Ixx3. So just I will write down the values. Ixx1 is 11, 25, 00, 000. Ixx2 is plus 83, 33, 333. Ixx3 is minus 1, 1, 3, 4570. Yes. So this is what we got. Now, if you simplify this, you are going to get the value as Ixx is 1094 8760. Yeah, millimeter power. So this is the moment of inertia of the composite section on the shaded area about the x-axis. Of course, suppose for the same problem, if they ask you to find the moment of inertia about the centroidal axis for this shaded area, then we have to locate the centroidal axis and then we can use the parallaxis theorem because you already know Ixx value. Only thing is you have to locate the centroid of this. So centroid where it lies, that we have to locate, and then we have to find out the Igx. We call it as Igx. So that can be